All right, ladies and gentlemen, today we're starting a new chapter on the urinary system, uh, which partially has to do with your liver, but mostly has to do with your kidneys. This is going to be a filtering system, how we clean your blood and get rid of the waste. This was originally from my class notes, which was spread across two different lessons, so don't feel like you have to watch this entire video in one sitting. In fact, I've added to this since then, so it's even longer, so it's more like 3 lessons at this point. I'm not sure at the time of recording this what the timestamps are going to be, but I will put them in Google Classroom for you. If you are watching this straight off of YouTube and you're not part of my classroom, well, welcome. And uh, the first section is purely my notes. The second section will be a live action version of myself doing a demo. So when you get there, you know you can take a break. Come back later on. And then after that goes back into my notes as the third section. All right, so let's get started. First off, a few important facts about the chemistry going on in your body. Uh, Amino acids, which is a chemical that you get from the proteins that you eat, contain a chemical called nitrogen, which is in and of itself not a problem. The problem is, as you probably know, you eat too much food, the food gets stored in your fat. Nitrogen doesn't. For some reason, nitrogen just does not get stored in your fat. So your body has to remove this nitrogen and then store the rest of the amino acid. And that's fine, but now you have this nitrogen floating around. In and of itself, not bad, but the chemical reaction that removed it from the amino acid also changed it. Now it's no longer just nitrogen. Now it's ammonia. You probably know ammonia as this chemical used to mop up your kitchen floor, right? Really smelly stuff, burns your eyes if it's too strong. Well, it's also very poisonous. It's toxic. So we need to get rid of that. Luckily, the liver has a way of converting it into a chemical called urea, which is significantly less toxic. Still toxic, still bad for you, but it's a bad for you that your body knows how to handle. Your kidneys are able to do something with that. They can filter that out. They know how they're described. So let's take a look at that liver really quick. If you take a look at this blue guy, it shows a big orange blob in the middle of his body. That is your liver. It's one of the largest organs in your body. Not the largest, but a pretty large one, and it is taking up a whole lot of the jobs. It actually plays a huge part in digestion, but we're not worried about that. It's a different chapter. Right now, this one is going to be attached to your blood vessels. You can see in this picture that the blood vessels go straight into the liver, and this blue stuff entering it represents the ammonia, the poison floating around your body. Your liver can cause it to undergo a chemical reaction, turning it into urea, like I said, less toxic. So, we can handle a lot more of that before you get sick. And it puts that back into your blood. And at that point is now your kidneys problem. Taking a look at this next picture, I got 2 pictures for you. The black and white one shows you the location of the kidneys. And if you look at your right side, his left side, it's hard to tell, but that kidney is actually slightly higher up, but otherwise in the pretty general location, same general location. And you can see 2 tubes, one for each kidney, coming out and going downward. Those are called the ureters, where all this waste that's the kidneys are getting out of your blood, well, that's going to end up becoming your urine. And it's going to go down the ureters and start filling up your urinary bladder, which is not shown in this picture. And we'll get to that part later. Taking a look at the blue guy picture, you can actually see that the kidneys are stationed not just in the middle of the body, but closer to the back, the posterior side, which is why in boxing it's illegal to hit that spot, right? There's not much there to protect it. The bottom of the kidneys are actually hanging out beneath the ribs. So, very dangerous strike there. So what is the function of these kidneys? Why would it be a really bad thing to get those damaged in a boxing match? Well, a couple of the jobs they do is to help regulate your water volume. And if you drink too much water, it'll get rid of the extra. Believe it or not, too much water can actually become deadly. not enough water, then your kidneys will actually prevent you from peeing out any extra water so that you keep what you have. It also regulates salt concentrations. Again, too much is bad, too little is bad. You actually do need salt in your body. One of the reasons is your nervous system requires it to work. Another reason is the kidneys themselves need it to work. We'll talk about that one in this chapter. And it'll help regulate your pH levels. Remember, kidneys are getting rid of things. So some of those chemicals will alter your pH. It gets rid of it. As it gets rid of chemicals, your pH will change. If it keeps chemicals, your pH will change the other way. Another job is to influence your red blood cell production. Remember, kidneys are cleaning your blood. So they're actually keeping account of your red blood cells. If your red blood cell count goes too low, say you got cut and you're bleeding, or you're in a car accident and you're bleeding a lot, or whatever, your kidneys will actually release a chemical called erythropoietin, which we learned about in the blood chapter. This erythropoietin is a hormone that will tell your bone marrow to start producing more red cells. And so red cell production actually starts with the kidneys. And as I've been saying, your kidney's job is to filter out toxic material, poisonous stuff that your body doesn't want, and gets rid of it. And that urea, at this point, you've probably picked out a connection from the name, is a major ingredient of your urine. Remember, urea was originally ammonia, right? It was changed. When you go to the bathroom, it leaves your body, it can actually change back into ammonia, which is why subway stations in Philadelphia tend to smell like someone spilled a whole container of ammonia out, because someone was peeing out in the staircase of the subway, and it converted back into ammonia, and that's what you're smelling in the air. Gross, I know. Anyway, back to the kidneys. So the kidney is in a bunch of different sections. We're going to talk about the jobs of each one momentarily, but right now I want to go through and just give you a little language lesson, because it turns out these words actually have meaning. Scientists use them for a reason. For instance, the word renal, which you see a lot on this page: renal cortex, renal medulla, renal artery, renal vein. Renal actually means kidney. It's a Latin word, so that's just what they called your kidneys. The renal cortex refers to bark, like the bark of the tree, and meaning the outside layer. So renal cortex literally means the outside layer of the kidney. Renal medulla means marrow, like bone marrow. And so that really means the kidney's marrow, this internal part. It's extremely salty, and that salt is going to help it do its job. So remember that. Renal medulla has a whole bunch of salt in it. We'll come back to that in a little bit. This next one, nephron, oddly enough, also means kidney, except this one's Greek. And so renal is Latin for kidney, nephron is Greek for kidney. And the nephron is a structure inside the kidney. So this is like the kidney's kidney, I guess, which makes a lot of sense, because this is the structure that's actually doing all of the work. And we're going to have a whole section on this, on how this nephron works. It's actually pretty convoluted. There's a bunch, really hard to see. I'll try to take my time with it. But notice part of it is in the cortex and part of it is in the medulla. That's important. The salt in the medulla is going to have a specific job for the part of the nephron that's in there. But we'll move on to that later on. Moving on to another word, renal artery. Artery is a blood vessel that leaves your heart. And in this case, this blood vessel is making its way to your kidney to drop off blood, to be processed, to be cleaned. And the renal vein is a vessel that goes back to your heart. So we are going to have a heart section and learning all about that. But the renal vein is bringing blood, now clean blood, it's been processed and cleaned, out of the kidney. And then all the stuff that you cleaned out of your blood has to go someplace. So that's what the ureter is for. It's all going to drain into this ureter, and which will make its way to your urinary bladder, and you'll pee it all out. All right. So let's talk about what these things do. All right. So overall job structures and things. Your kidney, which we have two of them, roughly fist size and bean shaped, hence the name kidney beans, because those kidney beans look like your kidneys. They're going to be on either side of your lumbar vertebrae, up against the posterior body wall. If you weren't here for the skeletal chapter or the directional terminology chapter, what that basically means is it's at the base of your backbone toward the back of your body behind you. All right. And each kidney has these three layers that we already talked about: the renal cortex, renal medulla, and what I didn't call out on it, the renal pelvis. The renal cortex, again, outer layer, the bark. Renal medulla, the marrow, is this cone-shaped section of which you can see in this picture we have a bunch of them. And this is where the urine is going to be secreted from, because all those nephrons I talked about are in there, which, by the way, you have more than just one. I forgot to mention this in that last chapter. You actually have thousands upon thousands, anywhere between, I believe the numbers were 900,000 on the low end, anywhere up to 2.5 million nephrons in one kidney. So that's a lot of urine being processed in those medullas. After that is what's called the renal pelvis. It looks like a weird opening there. It's a weirdly shaped funnel. It's actually made out of smooth muscle, meaning it's going to contract. It is a muscle. It's going to squeeze that urine out of the kidney and into that ureter we talked about. The process of squeezing, a muscle squeezing, is called peristalsis, which is a word that we will talk more about in the digestive chapter. But just picture how you would squeeze toothpaste out of a toothpaste tube. Right? It's the same motion. The renal arteries we talked about already. The artery that branches from the aorta, which is the largest artery in your body, and it's going to supply blood right to the kidney. That blood needs to be cleaned. Right? This is, I don't want to call it dirty blood, but it is not clean blood. The renal vein, shown here in blue, is going to remove now cleaned, filtered blood from the kidney, and it's going to go right to the inferior vena cava, which is one of the largest veins in your body. The aorta is coming from your heart. The inferior vena cava is going back to your heart. So these are direct connections to your heart. So kidneys are kind of a big deal. Going into nephrons, the kidney's kidney, if you will. Millions of filters. I mean millions. On average, million is the high one, but they have found up to about 2.5 million filters in the capillaries of the kidneys. Remember, capillaries are really small blood vessels, right? So these teeny tiny blood vessels coming in from the renal artery, and it branches into tiny, tiny, tiny capillaries. That is where the nephrons are doing their work. If you look at the picture below this, we see a section of the kidney zoomed in, and then a section of that area zoomed in again. So at the far right of this page, you are seeing red and blue. Those are your blood vessels. And you see yellow. Yellow is going to be the nephron. Here's another picture of it from a model. In this case, we are again seeing red and blue as blood vessels, but this time the nephron is white. And we actually see two nephrons in this picture, connecting to what we call collecting duct. Right, that's what's going to deliver urine to that renal pelvis. So let's talk about some structures here. First, before we, there's going to be an animation. Before we begin the animation, take a look at that almost round, like half circle on the nephron, the big yellow half ball. And inside there is a clump of blood vessels. All right, that clump of blood vessels is called a glomerulus. All right, it's capillaries, but inside this yellow ball. That yellow ball is known as the glomerular capsule. Glomerulus is the blood vessel. Glomerular capsule is the capsule enclosing the glomerulus. It's also known as the Bowman's capsule, but I try not to use that too much. I like to keep words connected. Coming out the back of that is what's known as the proximal convoluted tubule. Proximal meaning closer. Convoluted because it's all squiggly, and tubule means small tube. And then we got a section that dips all the way down. That's known as the nephron loop or loop of Henle. I like saying nephron loop, it's easier to remember. And then as that nephron loop loops right back up, we get another squiggly section called the distal convoluted tubule. So we have a proximal convoluted tubule in the beginning. Proximal means closer to the beginning. And then the distal convoluted tubule, meaning it's the tube at the end. And then that empties into what's called the collecting duct, which at that point, we're working with urine, right? It's now officially urine. So let's take a look at here. I'm animating it, and you see blood moving around. Now, it's hard to look at, but the blood enters the glomerulus, but then comes right back out. So something happens in that glomerulus. So second animation, but this time you see as the blood enters and don't look at the whole thing, it's confusing. Just look at the glomerular capsule, that Bowman's capsule. Right? As the blood enters, we see stuff exiting. Right? That is called diffusion, which I'm going to have a little demo to show you how that works. But remember diffusion from Bio 1, all the waste is spreading out of your blood vessels and into this capsule. And then the waste is going to move all around this nephron. Things are happening to it, we'll talk about, and eventually leaves. You see at the bottom, all the waste is exiting. All the clean blood goes one direction, and all the waste goes another direction. So let's get rid of the blood. It was confusing. Let's just look at this waste. Taking a look in this proximal convoluted tubule, the first little squiggly tube, you see little green stars, suns looking at. Those are supposed to represent nutrition, right? Turns out everything except your blood enters. Anything that you would have in your blood is going to enter there. So even good things that you want to keep. So the proximal convoluted tubule's job is to reabsorb the stuff that you don't want to get rid of. It's like, let me absorb everything out of the blood, and oops, I took too much. I need these nutrients. I need this sugar. I need these hormones. Let me put them all back into your blood. Excellent. Good job. And then down here in the loop of Henle, we have water. Remember, in the kidney, the nephron loop or loop of Henle is in the medulla, the renal medulla, which is super, super salty. Guys, have you ever put salt in your mouth, like just a lot of maybe a really salty pretzel or potato chips? It dries you out. Salt absorbs water. So this salty area is drawing water out of the nephron and back into your blood so you don't get dehydrated. And what you're now left with, let's take a look at the new animation again. All the waste leaving, reabsorb all the good nutrients, reabsorbing the water, and at this point, what you're left with is urine. Just straight urine. That's pee, right? It's the urea, any nutrients you didn't want back in your body, water that you can spare because it needs water to flow, and anything else that your body didn't really want, right? It's all going in there. So if you eat too much of something, maybe you eat way too much asparagus, well, certain chemicals in that asparagus you really don't want. And you eat a lot of asparagus, you get a lot of that chemical, which is why your pee starts to smell bad after eating asparagus, because that chemical is now in your pee. You didn't reabsorb it because you didn't want it. And just because I felt like being kind of a jerk, here is the blood added, and it looks like a hot mess. All right. This is actually happening in over 1 million different places in each kidney, right? At all times. This is really crazy. So at this point, I would say take a break, come back to the notes later on. Remember to timestamp because at the time of recording, I don't know what the time is on this. And come back to this thing. The glomerulus, I want to go into more detail when you come back. I'll wait. Okay, welcome back. So this is the glomerulus, that chunk of blood vessels, the capillaries that needs to be filtered, right? It is a bundle up of artery which gives off a filtrate. Filtrate is the stuff that you filtered out of your blood. It is good and bad stuff. If you remember from the last chunk of this video that I'm assuming you took a break, so let me remind you that this glomerular capsule, which is the next word down here, absorbs everything out of your blood, except the blood. All right, everything except the blood gets sucked out. So good and bad, and you have to put the good back and to get rid of the bad. And glomerular capsule, I just said, is the thing that is doing the absorbing. Hey guys, so right now I want to take an opportunity to remind you of something you learned back in Bio 1, diffusion, which simply is things spreading out. That's diffusion, just things spreading. In terms of biology, it was things spreading through a cell membrane. And that's what we're going to be seeing happening in this chapter in your kidneys, specifically in that glomerulus capsule. Things are going to be spreading through a cell membrane. So to give you a little demonstration of what I'm talking about, this is a tea bag. This is going to represent your cell. So the bag itself will be the cell's membrane. The tea will be all the things inside that are trying to spread out. Now, the tea leaves themselves are clearly stuck in this bag. They cannot get out of this bag. But particles of the chemicals inside of the tea leaves, they are going to be able to spread. They're spreading out. And to show you what this is, nice hot glass of water. Bring it down here. And this will happen. It has to be water because this happens in an aqueous environment. Right. Turn it around, find a better angle we can see. And you can actually see it looks like it's starting to bleed a bit. That is diffusion. Right? The chemicals inside the bag are able to diffuse, to spread through the membrane and into the surrounding environment. And that's what's going to be happening in that glomerulus capsule. Okay. Now I'm going to set this aside because that is perfectly drinkable tea. I'll let that finish diffusing. In the tea world, we call that steeping. And get myself set up here. This is going to represent your glomerular capsule, or Bowman's capsule, depending on which term you like better. Here's up here. That was looking kind of weird. Yeah, so this is going to be your glomerular capsule, your Bowman's capsule. And the pink straw is going to represent the proximal tubule. Officially, proximal convoluted tubule, but this one isn't as convoluted. It's nice and straight, nice and easy. That's the basic idea, though. All right. And this glass is just going to be something to catch the liquid as it pours out, because we're not actually going to have a ureter to eventually bring this to a bladder. Right? I didn't go that far. All right. So here I got a fresh tea bag. In this case, the cell isn't just one cell. In this case, this is going to represent the glomerulus, the bundle of blood vessels that are wrapped up inside of this capsule. So I'll keep that right in there. Nice and safe. See that? Everyone cool? Cool. Should I get a better angle if I can? Got some weird things written on here. That'll probably be the best view of it. All right. And pause for 1 second.
12 seconds later.
I'm back. So I almost forgot about some lab safety. This is hot water. So yeah, ignore the burn marks. I've had this in many fires. And I'm going to try to hold the water in so you can see it steep a little bit. Give it a second. This is not very waterproof, so put a plastic bag over it. I'm going to try to hold it like this. And no, I have not actually attempted this yet, so wish me luck. Probably not going to work out, but whatever. Bring this closer. Very smart of me. Let's mix technology with water. Alright, and no, we would not actually pour water into your glomerular capsule. Right? This would naturally be an aqueous environment or a watery environment in your body. And just like before, oh, got a little bit of a leak there. Oh no, my glue is melting. Just like before, we can already start to see some diffusion happening. The chemicals are leaving the tea bag. They're diffusing out into the capsule, filling that up. And this would happen much faster in your body, all right? That this is in slow motion. But when we are good and ready, which I'm about to be because this is very, very hot, the water will go drain out of the capsule through the proximal tubule. Ooh, very hot. See that? And then into the rest of the nephron, bringing the rest of the chemicals with it. In your body, what's really happening is this represented all of your blood vessels. Notice the tea leaves are still in there, which represents your blood. The blood is still in the blood vessels. All of this liquid was all the stuff that you don't want in your blood. All the extra stuff floating around, all the excess nutrition, if you ate too much of it, all of the bad chemicals that also come in the food, too much sugar, too much salt, too much everything, all the extra diffuses out into this capsule, and then down the proximal tubule to the nephron loop to the distal tubule, all the cool stuff that we're talking about, right? And eventually makes its way to your bladder, which I guess this would represent your bladder, where you would get rid of it through urination. So your pee really is all of the stuff that your body didn't want in your blood. Right. Back to your regularly scheduled notes. So now would be a good time for you to take a break. Maybe come back on another day. At this point, I just plan on pushing through and finishing it. So if you're as tired as I am, just stop. I will wait. Okay, welcome back. Assuming that you took a break, this would be your third installment of this chapter. And we are going to finish up talking about nephrons and how they connect to the kidneys. And then we're going to talk a little bit about your urine. This should be probably the smaller section. All right. So, quick review. Yesterday, you looked at, or assuming yesterday, you looked at how the glomerular capsule and the glomerulus work together to filter stuff out. Sitting before that, you looked at an animation of how the nephron actually works. So if you want to rewind and take a look at that really quick, be my guest. The proximal convoluted tubule is what connects to the glomerular capsule. Once all that stuff is filtered out, you need to move it, get rid of it. So it's going to go into this area. Proximal means closer to the capsule. Convoluted just means unnecessarily complicated. If you look at the picture, it's all squiggly. It is actually lined with a whole bunch of things called microvilli, which are, for now, think of them as tiny little straws that absorb things. And each microvilli, which we'll talk about more again in the digestive section, but each microvilli is dedicated to a certain chemical. So as a little straw, it will suck up just the chemical it's designed for. So if you have certain hormones that you don't want to get rid of, you have microvilli just for that hormone. If you don't want to get rid of some sugar, you have special ones just, when this is glucose, you have special ones just for the glucose, so on and so forth. They're going to absorb all the good stuff and put it right back into your blood. Continuing from there is the nephron loop, also known as the loop of Henle. If you look at the picture, that's what they call it there. It's the same thing. I prefer again nephron loop because it's a loop of the nephron. All right, so I like to go with that term. They're both official terms. Use whichever one you like. This is where you are going to reabsorb water. Again, you saw this in the animation 2 sessions ago. This is dipped down into the renal medulla. This picture shows it across a dotted line. That dotted line is where the medulla begins. Right. This is an extremely salty environment, and remember, salt absorbs water. That's why if you eat really salty things, you get really thirsty. Your mouth starts feeling really dry because it took the moisture out of your body and put it into the salt. And that's what this is going to do. The medulla is also full of blood vessels. So the water is going to be absorbed by the salt, and then the water is going to have nowhere to go except back into your blood. Right? This is a form of homeostasis, which is a chapter from biology, if you remember that, where if you drink too much water, you want to get rid of it, right? The loop of Henle only reabsorbs the amount of water that you need in your body. Any extra water stays in the loop and continues on, and you pee it out. Nice and easy. Then it goes into the distal convoluted tubule. It really doesn't have any kind of filtration job. It's just a carrying tube, right? It's just going to bring it over to the collecting duct. And in the picture, the collecting duct is that yellowy looking thing that is going to drain what is now urine, by the way, down into the renal pelvis. So let's zoom out and look at the kidney as a whole. All right, so we have the collecting duct. All of those millions of nephrons making all of that urine, they're all pouring it out into their collecting ducts into one central location here that I have highlighted in green is the renal pelvis, which channels the urine into the ureter. We talked about the renal pelvis a couple sessions ago. It's basically a funnel, all right? The millions of nephrons are all pouring it in there, and it gets going to get funneled into the ureter, which I now have highlighted for you to see. That ureter is going to now start draining into your bladder. This was a real picture, but I understand some people prefer the more cartoony pictures. It helps them understand better. So here's a cartoony version. What I have highlighted, again, the renal pelvis. And all that urine in there will get funneled into the ureter, which is now highlighted. All right, zooming out again. Right now you see the body, you see the 2 kidneys that you have, and the 2 ureters. And all of that urine that is pouring down those tubes are pouring into your urinary bladder. You see how the words are connecting here? Urine is going into the ureters, which goes into your urinary bladder. And when it's full, you are going to urinate to get rid of the urine. Like the doctors choose these words so that it all connects and makes sense. Right? And the urine leaves the bladder through the urethra, which is the passageway that we pee from. And men and women, being structurally different down there, are going to have different size urethras. Men have an exterior urethra, or urinary organ is going to be slightly longer. Women, because you have internal reproductive organs in the way, your urinary bladder is going to be a lot smaller. But it's also going to have a lot more pressure too. Just an odd fact for you, in case you're interested. But I care right now more about the urine itself because there is some cool, weird medical things about your urine. First off, you can tell how hydrated you are. Typically, you can tell whether or not you're hydrated by whether or not you're thirsty. Clear sign, but sometimes you don't really notice it. Your body doesn't tell you right away. If you're really busy, if you're super active, sometimes your body waits to tell you. So if you keep being active, you don't find out. Happens all the time in the military. So they're actually they're trained not to depend solely on their thirst. Soldiers are trained to depend on the color of their urine. If you have a whole lot of water in your system, that means you have a lot of extra that's going to go into your urine. That extra water is going to make your pee look clear. Uh, if it's more of a yellow, that's pretty average, normal. But if you start getting to a dark yellow or even amber, now you are starting to show signs of dehydration, meaning your body is not putting water into your urine. So by volume, you now have more urea, which is that chemical we made from the ammonia. Remember that, right? That poison that you gotta get rid of. You now have higher levels of urea by volume, making it darker and smellier. And then you start getting into an orange. Now you are severely dehydrated and you need to go seek a doctor, right? Because at this point, chances are it wasn't the decision. All right, something's wrong. Uh, Oddly enough, you also get some other colors too. They're kind of strange. So just to go through some examples. Turns out, by the way, you can get like every color of the rainbow for different reasons. If you see a cloudy white color, that means you probably have some kind of infection, most likely a urinary tract infection. Um, the cloudiness is actually a bunch of white blood cells. When you have an infection, some kind of bacterial infection, your body sends white blood cells to the area to fight it off. So now you have a lot of white blood cells in your pee, making it cloudy looking. If you start smelling some sweet smells while you pee, that's sugar, glucose. People with diabetes tend to have a problem not being able to maintain their sugar levels, and they, without insulin, usually accidentally pee their sugar out when they want it to keep it. Insulin's going to help you keep it. So now diabetics tend to smell the sweetness. One of the signs that they need to get their insulin ready. If you see pink or maybe even red, you probably have some kind of internal bleeding. Not good. Talk to a doctor. Unless you've been eating beets. The root vegetable beets actually gives a red dye that your body doesn't want. So your body gets rid of the red dye, turning your pee a certain pinkish red. And pay attention to your diet. If you haven't been eating beets and you see red, speak to a doctor. Green. Overabundance of asparagus. Again, has that chemical that your body doesn't want. If you eat way too much of asparagus, your yellow pee starts turning into a green pee. Or St. Patty's Day, if you're drinking a whole lot of beverages, we'll say, that tend to be dyed green around St. Patty's Day, and you drink way too much green dye, again, your body gets rid of it and turns your pee green. So nothing to worry about, just pay attention to your diet. Blue. Blue is actually a cool one. You can have blue pee, but not everyone can do this. This is a certain kind of mutation where some people have an inability to break down this amino acid called tryptophan. Tryptophan is an amino acid which is an ingredient in your proteins, and you can get it from eating certain meats. Turkey is famous for it. That old myth that if you eat too much turkey, you're going to fall asleep because cooking tryptophan knocks you out. That's a myth. No, you fell asleep on Thanksgiving because you ate too much in general. Right? Tryptophan itself is just an amino acid, and some people can't break it down, and it ends up coming out as a blue color. And here's one that you do have to worry about: dark brown or black urine. That is copper poisoning. Right? Certain pots and pans that cookware are made out of copper. Not that big of a deal because it comes with a coating, usually a non-stick coating. You're fine. But older pots and pans, the non-stick coating starts to chip away, breaks away, and people are now cooking directly on the copper. That's a problem. Right? The copper molecules go into your food, and now you're eating copper, which your body doesn't want. Now, at first, you're not going to notice anything, but you keep eating out of that pan for months at a time. Eventually, it's going to build up, and you are going to poison yourself, and you will see the effects as a dark brown or black urine. Right? There are other things. I thought those were just the more interesting things. But feel free to leave other examples behind in the comments if you happen to know any. And that is it for the notes. Thank you for coming. If you are in my class, take a look at Google Classroom for assignments to go along with these notes. If you're not in my class and just hanging out on YouTube, thanks for watching.